Okay, so let's get started with the review. This first one, they want to put a table to this. So I know that when both, let's see, P is shopper by produce and shopper playing with credit card, when those both happen, it's 45%. So if you look at the answers, these are the only two where that's possible. Okay, so let's see what else. Let's see what's different. So those are the same. So let's find out when it's P but not C, right? That's what that is. P but not C. So P but not C should be not 60. It should be, this one's got to be P because that one looks right. I toss a penny, observe whether it lands heads up or tails up. Suppose penny is fair. Um, does this mean every occurrence of head must be balanced by a tail in one of the next two or three? No, that's definitely not true. If I flip the coin 10 times, it would be almost impossible to obtain 7. No, that could happen. If I flip the coin many, many times, the proportion of heads will be approximately 1/2, and this proportion will tend to get closer and closer to 1/2. That sounds like the law of large numbers. Goes half will leads to heads and tails. That's not necessarily true. Okay, so this one is just, this is not too bad. So add that up, 50%, 60, 70, 80. So this has to be 20%. Has to add up to 100% to be a valid probability model. Particular game, a fair die is tossed. If the number of spots showing is either 4 or 5, you score 1 point. If it's 6, you score 4 points. And if the number of spots showing is 1, 2, or 3, you score 0. So 1 through 3 gives you 0. 4 or 5 gives you 1. And 6 gives you 4 points. You score 4 points both. They seem to be independent, right? Because each time you roll a die, that's independent. So the two probabilities, I want to score 4 points, so that'll be 1 out of 6 times 1 out of 6. Those are independent events, so 1 out of 36. One's a Dodge or has 4 wheels. So Dodge, what's the probability of that? So that would be Dodge is 30 out of 125. And 4-wheel drive is 80 out of 125. So I'm going to add those together, but I'm going to subtract the overlap. So if you think about the 4-wheel drives, it's these folks. Dodges are these folks. So it looks like you double counted the 20. So whatever that is, 110 minus 20 is 90. Not so bad so far. So you randomly select owner has a Chevy and, so Chevy and has a 4-wheel drive. So that would be 32. I don't think I have to do this. I didn't look at the answers. Okay, so maybe I should read the question. Which of the following is true about the events? Okay, are those mutually exclusive? Well, so if you look at that, that's not 0, so that's not, can't be it. Mutually exclusive is not. But they are independent, so how would I prove independence? So let's just plug into a formula. So P of A in this case is going to be, let's say Chevy. If they're independent, it should be probability of Chevy, given that you have 4-wheel drive. Okay, so this probably Chevy is just 50 out of 125. And given you have 4-wheel drive, so there are only 80 of those guys. Chevy is 32. So I don't know. Let's just double check. Doesn't look like they are, but maybe they are. We'll see. Okay, so 50 divided by 125 and 32 divided by 80. Oh, so they're independent. So they are independent. Nice. Wasn't sure that was going to happen, but those numbers worked out. Okay. I could have crossed that one out because it said it's mutually exclusive. It's not. So event A will occur 0.5, B is 0.6, probably both would be 0.1. So they can both happen, so it's definitely not that. Well, let's do probability of A. Okay, so we're going to go probability of A should equal the probability of A given that B has already happened, right? So the probability of A is 0.5. And given that B has happened, so I guess that's 0.6 is the denominator. That's the given. Given B has happened, which is probably that A happened. So out of those 0.6, how much of that is overlap or both? In other words, so 0.1. So 0.1 divided by 0.6 is 1/6, which is not 0.5, so that is not equal, so they are not independent. So complementary would mean like the opposite. That can't be because there's overlap and 0.5 and 0.6 don't add up to 1, so they're complements. Let's draw a Venn diagram of this. I think it'll help us on this next one. So 0.1 is the overlap. A is 0.5, so that would be 0.4. That's not the overlap total of 0.5 if you add those up. And 0.6, so this would be 0.5 would be no overlap, but with that, okay, so 0.6. So A or B always occurs. So that adds up to 100% if you add that. So that one is true, I think. Okay. Ignoring twins and other multiple births, assume that babies born in a hospital are independent random events with the probability of the baby boy, probability that a baby is a girl is both equal to 0.5. What's the probability that at least one of the next 3 babies is a boy? So at least one is really tough to do. So if you think about that, so maybe the first one is a boy and the next 2 are girls. I'm just giving you like, so we could calculate that number, 0.5 times. Maybe the second one is a boy and the other 2 are girls. Maybe the third one's a boy and the other 2 are girls. Okay, so that's all the cases of getting one. Then we have to do all the cases of getting boys, boys, girl, girl, boys, boy, boy, girl, boy. So that's all the cases of getting 2 boys, and then getting 3 boys would be this. So we'd have to look at, oh, it's just so much work, right? So we'd have to calculate each one of these and add them all up. We could do that. We certainly could. But that seems like a lot of work. And man, sometimes it's almost impossible. That's only 7, different things. But man, I mean, it could be like at least 1 out of 12. And then you're talking, I don't even know how many, right? So many different options there. So I don't think that's the way to go. I think you want to use the complement. Whenever it says at least one, the opposite of that, the complement of at least one, complement, would be the probability of none. So the complement of that should be probability of none. Well, none is easy to get. So that's just girl, girl, girl. No boys. So that'd be 0.5 times 0.5 times 0.5, whatever that is. So let's get your calculator out. If you don't know that one, you might have to type it in. 0.5 third, oops, 0.5 to the third, 0.125. So this is 0.125. So the complement, so to get at least one, it'd be 1 minus 0.125, which is 0.875, I believe. So that would be our answer. By the way, if you added up there's 7 of these, they're all 0.125s. So 7 times, I'm guessing this is true, 7 times 0.125 is, oops, 7 times 0.125 should be 0.875 as well. So you could actually do it this way because there's a small enough number, but my goodness, just so much easier to do. At least one. The complement or opposite of that is none, because all the other cases have one or more boys, but no boys is the complement or opposite of that. Not having boys would be only girls. The probability of randomly selected adult having a rare disease, which there has been developed, is 0.001. So disease, I'm thinking, no disease. So 0.001, so this is 0.999. Probably the test would be positive, indicating that the person has that disease is 0.99 for a person with the disease. So this is positive, would be 0.99. And this is really bad here. So this is 0.01 for the negative. Gotta be right. And 0.02 for a person without the disease. I guess it's saying positive. So positive would be 0.02, a 2% chance. And negative, which is the correct decision there, is 0.98. What is the probability the individual has the disease? So has the disease, okay. Okay, so let's get all the n values here. So I'm just gonna multiply them here. So 0.001 times 0.99, oops. For some reason it's just not that 0.001 times 0.99. I'm going to do all 4 of them times 0.01. And then 0.999, I'm doing them in an order, times 0.02. And then 0.999 times 0.98. Okay, so we have, this one is 0.00099, 0.00001, I think. Okay, 0.01998. Those are all pretty small. And then 0.97902. Just for fun, let's add those up. I want to make sure I didn't make a mistake here. That plus that plus that plus that. Adds up to 1. That's good. That means it's a valid probability model. I mean, well, this is, just tree diagram, I guess, but it's the test we do for that anyway. Okay, so we have to read this question carefully. If randomly selected person test is positive, so positive would be these folks, and these folks. So those are the two groups we're looking at. That's my given information. So if I do a fraction there, the denominator is going to be 0.00099 plus 0.01998, I think. Yeah. Okay, so the numerator, what's probably the individual actually has these. So of those two that I just added, the two positive result folks, the one to have it is 0.00099. And so we get it. It's E. I think that's right. Event A occurs with a probability of 0.3, and event B occurs with a probability of 0.4. If A and B are independent, then if you multiply 0.4 times 0.3, so that one looks really good, right? Yeah. So the probability of A is 0.3. So if B has happened, that shouldn't affect it, so that's good. Probability B is 0.4, so if A has happened, it shouldn't affect it, so that's good. I think they're all, I think it's all of the above there. It's nice. Okay. Here's a word problem for your response. Mr. Lee conducted a taste test for 4 different brands of chocolate chip cookies. Below is a two-way table that describes which cookie each subject preferred and their gender. Okay, so find the probability that selected subject preferred brand C. So we know there are 24 of those folks out of 94. Now you should type that in your calculator, get it. I'm just going to leave it like that, just so we have it. Find the probability that the selected subject prefer brand C, given that she's a female. So denominator, so we have a total of 36 females. So, yeah, so 36 females. And out of those 36 females, brand C, C is 13. Are the events preferred brand C and female independent? So let's just do it this way. So probability of preferred brand C should equal probability prefer brand C given that you are female. So prefer brand C is 24 out of 94. Oh wait, did we just figure out these two things? We just figured out that one and give me a female brand C. So 13 out of 36. Well, I mean, that was almost 3 times as much. That's not nearly 3 times as much. So those aren't equal. You can type in your calculator, but they don't work. Are the events prefer brand C and female mutually exclusive? Brand C and female, there's 13 cases where that happens. So we would say no. Why would you say no? Because it happened 13 out of 94 times. So the probability of brand C and female should be equal to 0 if they're mutually exclusive. If a random sample of 2 subjects is selected, what is the probability that neither preferred brand A? So I want to pick 2 individuals. I'm going to multiply these 2. If random sample of 2 subjects is selected, what is it? So, okay, so the first subject did not prefer brand A, so that would be 17 plus 24 plus 27, so 17 plus 24, oops, 17 plus 24 plus 27. So there's that many folks that did not like brand A. So that would be divided by, so that first one would be 68 divided by the total of 94. once you've chosen the first one, these are not independent events. There's no replacement, I think, with these folks. So I think the second would be 93, and there'd be 67 non-A's left. So whatever that multiplies to make would be our answer, I believe. Probability the randomly selected person in the United States is left-handed is about 0.14. Among the 28 students in Mr. Heath's AP Stats class, 8 are left-handed. About 0.14. Okay, so 8 are left-handed. Okay, so random number table is simulate the proportion of left-handers in a class of 28 students. Okay, so if this is correct, like we're saying, we're basing our probabilities off that. So you might say you're going to label left will be numbers 01 through 13. Oh, how about 00 through 13? 00 through 13. Right will be 14 through 99. I'm taking 2-digit numbers at a time. You probably want to say that. Okay, so we label them first. Then we do the, we don't have to perform the calculation. So step 2, go left to right, right, 2 at a time, 2 digits at a time. What do we do about repeats? Are they okay? We can ignore repeats. I'm fine with that. I think you might be able to go either way on this one, but we're going to ignore repeats. So what's our stopping mechanism? And so we're going to 28. So use the random number table to choose 28 unique numbers. Okay, so record or count how many left-handed lefts out of 28. Repeat many times. Something like that. Probably a good idea to look at the what they wrote. Here's what they wrote, so you could read through that in case I forgot something. Okay, oh, I guess just that first part, right? Okay, so okay. Next part, the graph shows the actual simulation of 100 students. So where does, let's see, 8? I think it was 8, wasn't it? Yeah, 8 are left-handed. So number of lefties is 8. So that happens in 4 out of the 100 cases. By the way, what does 0 represent? That means in one trial of the simulation, 0 of the 28 students picked randomly were left-handed. Estimate that there would be 8 or more students left-handed in class of 28 students. So there's a 4% chance. 4% chance that happened from the results of the simulation. Because you get those 4. What do these results suggest about the proportion of lefties in Mr. Heaton's class? because, I'll just say the words, because the result was so improbable, less than 5%, a 4% chance of that happening by chance, we think that, what's the question? I mean, I don't know that we're saying he lied. I mean, I think it's just a case of super unusual. That, oh, I know what it is. So maybe we think that 14% figure is not accurate. I think that'd be right. So let's look at 12. Only this suggests that the number is unusual. Okay, that's certainly true. I would question the number. I would question the 14% because our results seem to say that doesn't seem accurate. You draw 2 marbles at random from a jar of 20 red marbles and 30 black marbles without replacement. What's the probability that both marbles are red? So the first one would be 20 out of 50 times. These are not independent events, but you still multiply, and then 19 out of 49. Those are dependent events, and you multiply those. Wile E. Coyote is pursuing the Roadrunner across Great Britain towards Scotland. The Roadrunner chooses his route randomly, such that there is a probability of 0.8 that he'll take the high road and 0.2 he'll take the low road. Okay, that's not contingent, so we're going high road. You should always take the high road, right? And low road. Just in life. Okay, so 0.8 is high and 0.2 is low. If he takes the high road, the probability that catches him is 0.01. Okay, so catch is 0.01, which means 0.99. So not catch. And then for this one, it would be catch and not catch. And this one was 0.05 and so you should take the high road. They took the high road given that he was caught. Given that it was caught. So we're looking at this one and this one for sure. So let's get those probabilities. That would be 0.01 times 0.8 is 0.008. And 0.2 times, just to make sure. So just get it's hard to do stuff sometimes. 0.2 times 0.05 is 0.01. So my denominator is going to be 0.01 plus 0.008. What's probably took the high road, so that would be this number, the 0.008 would be in the numerator, and then you just type that in your calculator, I'm sure you get some kind of answer there. 0.444. Okay, that's your lesson for today, or your review, I guess.